All right, welcome back, everyone. So today we want to talk about out-of-order execution. A few things. First of all, happy Halloween, right? Second is those of you who are following Dodgers, congratulations. If you're following Yankees, also I think you've been scared enough. Like it was a scary show last night. And also hope you had a great quiz one. We're gonna release the solution soon. It's going to be a detailed rubric, and we typically try to make sure that different parts are graded independently, so that if you make a mistake in one part, it's not gonna kind of like accumulate and go over the second part. And then you will have the opportunity to do regrade requests and ask for more questions and all that. And usually what I've found in the past years is that first quiz is more difficult than the others because of the formatting, that you're not familiar with the formats. Second and third quiz becomes a little bit easier for people because now they get a little bit more familiar. Part of it is because it's kind of a time crunch. It's like you have to be quick and kind of write things down. And one reason for it is intentional, because we want you to be able to think fast. But yeah, again, it's kind of like a specific format that you get used to it as you do more. And then there will be also opportunity for you to kind of, if you didn't do well, first of all, this is just 1 out of 3 quizzes. Hopefully there are others that you can do better. And then also the projects and all, you have opportunity to have both bonus points, and also kind of the grade is kind of fairly distributed among multiple components. So if you didn't do well in one component, it's not gonna ruin your score or anything. So there is plenty of opportunity, but I think most of the time people do really well. So I don't think like we have to see the scores, of course, but usually most people have like really good averages. But yeah, I think that's it for quiz. And then don't forget, next quiz would be sometime in, I think, week 7 or 8, which is going to be most things about branch predictor, and then things that we're going to discuss this week and next week. So this week we have an important topic to cover, and that is out-of-order execution. Yeah. Question is, how many computer assignments are we going to have? And the answer is 3. Where is my? Okay. Yes, actually, on that note, we're going to release the second computer assignments this week. The second computer assignment is a little bit different. So it's going to be a competition in some sense. So it's going to be a championship. You have to design a branch predictor, and your branch predictor will be compared against your classmate's branch predictor. So we're going to give you a test, and you have to run your test. And whoever does better in the test, they will rank higher. The way that we're going to grade it, though, is that we're going to ask you for kind of we're going to give you a baseline code, a simple branch predictor. You have to improve that. If you can improve that, you're going to get the full grade regardless. Okay, so even if you kind of rank last, you're going to get the full grade. But if you rank higher, you're going to get more bonus points. So doing better gives you more bonus points. But if you want to do minimum and just do a branch predictor, you're going to get the full grades. So don't worry if like others doing better than you. Yeah. Correct. So we're going to give you the skeleton. The skeleton actually does everything. So you just need to replace the branch predictor with your branch predictor. We're going to actually even give you a skeleton code for a branch predictor. You're going to upgrade that. Yes. No, the run for what? Like, we're not gonna. So the question is like how long the branch predictor, like per prediction? No. So this is actually, the competition was part of a conference a few years ago. One thing you want to consider for your branch predictor is other considerations like timeliness or the storage overhead or the power overhead and all those things. For this particular one, we're not gonna consider those. So you can consider that you have infinite time and storage. Can you do the best? There is actually a theoretical work on like what is the best possible branch predictor you can ever design. So if you want to go that far, you can do that as well. Yes. The question is that are the coding assignments worth the same? It's actually no. So the first was 40% of your, so I don't know, like 30% or something is just from the whole grade is your computer assignments. And then there will be 3. The first one will be 40%. The second one is 20%, and the last one will be also 40%. So 1 and 3 will be 40%. This one is only 20% because, as I said, the baseline design is very simple. Probably takes you like 3-4 hours at most to do just like to get the full grade. But if you want to do the bonus, I mean, sky is the limit, right? So you can spend a lot of time. Yes. The percentages of the, so the question is about the percentage of the grading. For the CA is in the last lecture 1, but between the CAs is actually on the project description of this particular project, you will see that, yes. And you also see that, because I'm gonna give you bonus point depending on your ranking, you're gonna see that as well. So like if you're in the top 50%, you're gonna get like 5%. If you're in top 20, you're gonna get like 8%, and if you're top 5%, you're gonna get like 10% or something. There will be also a video I recorded for your design of the branch predictor. We covered branch predictor in the class, but I gave you a little bit more on that lecture, which is gonna be posted today as well, to kind of give you some little bit more information on how to design your branch predictor. So watch that before starting your project, okay? All right, so let's talk about out of order. Last thing that we discussed last time was superscalar. By the way, like the lecture last time wasn't fully recorded, unfortunately, because I forgot to record it on Zoom after the break. I posted the part that we missed on the website as well, so you can watch that. For those of you who were in class, you saw everything. But for everybody else, make sure to watch that as well. Okay. But what we discussed was superscalar in the second part of that class. The idea of the superscalar is that can I process multiple instructions per cycle, okay? So the design was like essentially replicating everything that I have multiple times, n times. And this way I can achieve higher IPC or lower CPI. But there is a disadvantage and an advantage. There's always trade-off, right? So the disadvantage was there's more complexity, there are more hardware resources needed, and so on. And the biggest problem was there are lots of dependencies between instructions, and I need to figure out that. But essentially what we can do is that we can go past this, what we call scalar processors, which what we have learned so far, and that was the IPC at best could have been 1. Now we can have IPC better and higher than 1. But one thing that really kind of limiting us was the fact that we couldn't do what we call out-of-order fetching, which means that we always need to go by program order, and that limits us significantly in terms of which instructions can we run, okay? So we want to be able to kind of get rid of these limitations by running instructions out of order, randomly from any sort of sequence that we want. Of course, that will cause lots of issues because we need to now make sure that the program also runs correctly. But the goal of this lecture and generally this design of what we call out of order execution is that being able to run instructions that are independent from each other such that we can fill up our superscalar pipeline such that we can get the best performance out of our design. That's the goal of the out of order, okay? So kind of like where we are now, the status quo is that we have a superscalar processor. Usually superscalar is like n equal to 2 or 4, which means that I can run 4 instructions at the same time for each stage. And ideally, I can get IPC equal to n. and we want to be able to kind of like fix this other raw hazards, such as, you know, load use hazard and raw data hazards and all. And then since I have a good branch predictor, I can probably fix many of the control flow hazards as well. In most cases, I can get 90% accuracy. But the biggest thing that is kind of like limiting me to going further than this is the fact that I cannot fetch many instructions all at the same time because of the dependency between them. Okay? So let's see how we can actually do this. So the idea that we are going after is that what I do now is that I do PC plus 4, PC plus 8, and so on. So I only have, like, let's say if I have a 2-issue superscalar, I can only fetch these 2 instructions, and if they are somehow dependent to each other or dependent to the previous, the only thing I can do is install it, okay? But now what I want to do is that I'm gonna define a new thing called instruction window. So I have a bunch of instructions, okay? So I have lots of instructions. What I can do is that I say that, okay, instead of just looking at these 2, why don't I look at a much larger possibility of instructions? And then instead of like saying that, okay, either these 2 are dependent to each other or not, I can say that I can choose 2 out of any of these instructions. As long as they're independent to each other, I can fetch them and I can push them into the pipeline. So for example, I can select this one and then push them into the pipeline. And if I do that, then just by sheer of probability, there is a very, very good chance that any given cycle, I can execute multiple instructions, let's say 2 or 4, whatever the superscalar is, okay? So in other words, I'm trying to increase the possibility of searching through instructions and finding independent instructions and push them into the pipeline. And the reason that I can do this is that instead of just searching for 2 instructions, now I can search through a large list of instructions, okay? So this kind of like, the idea is very simple, but there are tons of problems because of this. First of all, how do I search? How do I kind of reorder them back? What happens if we need to flush? And there are tons of these other problems that I need to solve. And that's the idea of what we call out-of-order execution. Okay. Going back here. Did you have a question? Okay. Yeah, so there are going to be lots of questions, right? So first of all, how do we know who is available, who's not dependent on the other? What's the criteria for dependencies? Would this create even more problems? If there are more problems, what should we do? What about the hazards? Are we going to have hazards or raw data hazards? What about branches? Are there new hazards? So there are tons of these questions as long as we kind of like make this kind of tiny change that instead of going by PC plus 4, I'm now telling you that you can do anywhere between PC plus n or PC minus n. So now you have a window of instructions, okay? So there is these problems that we need to solve in order to fix this, okay? So this is basically the idea of what we call out-of-order execution. And we're going to talk about 3 main things. There are a few more details, some of which we're going to talk about more next week. But there are 3 main things that we need to fix and we need to provide in out-of-order execution. And these 3 things are, number 1 is that how do we track instructions in order to see who is independent from each other. In other words, who is available and can be executed. So we need a mechanism for tracking instructions. The second thing is that we need to have a mechanism for data hazards. And as we're going to discuss, there will be new hazards such as write after write and write after read that we didn't have in order processors. So we not only need to fix old hazards such as raw and load use, now we need to also fix these new hazards. And then we need to be able to do forwarding and all that. And you will see that the forwarding is slightly different in this case. And lastly, and then this is the biggest problem that we're going to have in out-of-order, is a mechanism for recovery. And the reason for this is that, if you remember, we do lots of speculation, right? So for branch, for example, we say that, oh, let's assume that this is going to be taken or this is going to be not taken. Let's just start executing things. And now things are more complicated because now I also executed things out of order. So I need to flush lots of things. It could be many, many instructions after or many, many instructions before. So there will be more challenges for the recovery and flushing instructions, okay? So this is basically how we're going to design our systems. Our system is going to be basically very similar to what we had before in terms of pipeline stages. Still a pipeline stage design. But what we're going to do is that we're going to have this kind of three-step approach, okay? So what we're going to do is that we typically call this front end and back end. The front end would be what we call an in-order front end, which means that our fetch and decode is still going to be in order. So we're going to fetch 2 instructions or 4 instructions or something else at a time, okay? And we're going to decode them also in order. So nothing changed at this front end of my design. What will happen is that I'm going to have some form of a buffer here that I'm going to push things here, but now I can execute them out of order, okay? So essentially, I think about this as a long queue that I can fetch things in order. I put this in this queue, but from this queue, I can choose any one that I want. No longer needs to be in the order that I put them into the queue. I can just choose whichever is available, okay? So in other words, my back end, my execution would be out of order. So when we say out of order, doesn't mean that everything is out of order. It's still my fetch and decode is in order, but my execution is out of order, and I decouple these two from each other using some form of a buffer, a large queue that we're going to call reservation station or issue queue, okay? So I'm going to execute things out of order, and I'm going to complete them. And what we're going to do is that we're going to have another buffer here called reorder buffer, that we're going to put them back in the order that they were, okay? So think about this as like a long list that we're going to pick things out of order, execute them, but then put them back in the order that they were. And then we're going to kind of complete them, which we call them retire, and we're going to retire them again in order. So things going to be read in order, going to be executed out of order, but then they're going to be completed and written back again in order, okay? And the reason for this is that we want to maintain completeness and correctness. Otherwise, if we kind of complete things out of order as well and write things out of order, we're going to have lots of issues because if you're writing to the same register, for example, you want to write to the same registers in the order of the program. Otherwise, your values would be incorrect, okay? So let's talk about these 3 things one by one. I'm going to start talking about this last one because this is the most important one, and this is kind of the reason that we follow this in-order front end, out of order back end strategy, okay? So let's actually see what happens when we have something like a misprediction, okay? So I'm showing you a sequence of instructions. The instructions kind of going down this way. So let's say we have I1, I2, all the way to I9, okay? What we learned in the class was that we're going to have, we're going to, issue and run these instructions one by one, and some of them will be completed, and some of them will move forward. Let's start with like an in-order processor. So let's say, for example, we start with these instructions one by one. So this one goes to the pipeline, then this one, and so on. Let's say at some point we are looking at this pipeline, and this I1, I2, and I3 are already completed. And then in the pipeline, we have I4, I5, I6, and I7, okay? So let's say, for example, now that I4 was a branch, okay? So it was like branch equal, okay? And let's say that we predicted that this branch should be not taken, okay? So as a result, what we would do is that we are going to fetch I5, I6, and I7, okay? And let's say, for example, we resolve the branch in the memory stage, which means that if we realize that this branch should have been not taken, at the memory stage, we're going to realize that, and we're going to say that, okay, these 3 instructions needs to be flushed, okay? And we already discussed how do we flush them, right? So we replaced them with the no-op, with the bubble. We had those muxes and all. So we flushed them, and everything was good. That's all we discussed so far in the class, right? So we flushed them, no problem. And then we're going to maybe continue. Let's say, for example, the next instruction, let's say this branch should branch into this instruction. So we're going to start this fetching the correct instruction, and we're going to continue. Okay? So far so good. This is what we covered in the class. This was part of like your quiz one and all that. So hopefully by at this point you understood how this would work. Okay? Now let's talk about out of order execution, and let's see how out of order execution could cause new problems. So let's revisit this problem. But now let's imagine that when I'm start executing these instructions, okay, I can execute them out of order. I no longer do I1, I2, I3, I4. Maybe I do I1, I2, I7, I8, or something like that. So the sequence of instruction that goes through the pipeline and the results can be completed, not necessarily follow the same numbering that we have, okay? So the format that we might have, it would be something like this. That let's say I have, again, the sequence of actual instructions is I1 to I9. But let's say, for example, the instructions that being completed, that we went through the pipeline and completed are now I2, I1, I2, and I7. So I7 is kind of like executed out of order and already been completed, okay? And now let's say, for example, within my pipeline, I have I4, I3, I5, and I6. And again, you see that things are kind of shuffled, right? So used to be I4, I5, I6, I7. Now it's I4, I3. So essentially, this 3 and 7 has been replaced or switched, okay? So now let's say that we have the same problem, which I4 has been a branch, okay? So I4 is a branch, we predicted not taken, and now we realize that, oh, okay, we need to flush, okay? So with the existing design, what we would do is we can say that, okay, these guys needs to be flushed, although I3 technically doesn't need to be flushed. I3 is actually prior to I4, so we don't even need to flush I3. But let's say for now, we flush everything. So that's great, we can do that. But the problem is that now we're going to have I7, and I7 is already completed. There's nothing that you can flush off of your pipeline, because I7 actually happens way before I4, and it's already completed, and it's already been written back, and all that. So how we can even flush this when it's already completed? And that would be the problem that we're going to face with out of order execution, because there's nothing there in the pipeline to even flush because we already execute this, okay? So this would be basically the problem that we're going to face in out of order execution, that we need to be able to flush things that happens even before the instructions that we have. Any questions so far? Great. So in order to fix this issue, we're going to have a new concept called retire, okay? So in the past, we have instructions that were being completed, okay? So we run an instruction, the instruction goes to the execution stage, goes to the memory stage, and then is completed, so it's written back to the register file or written back to the memory, okay? So that was the notion that we have, that the instruction is complete, now we can go to the next instruction. Now we have, since we have kind of two steps, there is one step that the instruction is getting completed, but there are prior instructions before this instructions that may not be completed yet, okay? As a result, we now have two separate stages. One is called complete, the other one is called retire, okay? So instructions can get complete out of order, so you can push them into the pipeline, you can execute them, but then you need to save them somewhere, some temporary register, some temporary buffer that they are kind of staying there, but they're not yet you don't yet get rid of them. We call this complete, but we don't retire them. We only retire them when it's safe for this instruction to be retired. In other words, we only retire them when it's safe for this instruction to be written back. When do we do that? When all the prior instructions to that instruction has been retired. If everything before that has been retired, now it's safe to get rid of this instruction as well, because that gives you exactly the same thing that you had for in-order execution. Okay, there are tons of questions. Yeah. So the question is, when we complete, what exactly do we do? That's exactly what we don't do. We don't write back. We write back into a temporary registers, and from that temporary registers, then we write back to our register file. So the difference between retire and complete is in complete, we have the results, but we don't write that result back into our registers and memory. We write it into some temporary register we call reorder buffer. And then from that reorder buffer, when it's safe to retire, then we're going to write it to the register file and memory. Yeah.
So are we not write back to registers, or are we also just not writing to memory in general?
So the question is that, is it just not writing back to registers, or is it also not writing to the memory? Both. So we're not going to write to anything that is permanent. We're going to write, so not going to write to PC, not going to write to register file, not going to write to memory. Yeah.
So basically, depending on the instruction, we may stop before the memory module. Stop before.
Yes. So the question is, how do we implement this? I'm going to give you the details of how do we implement this. Yes. I'm going to show you the pipeline, the data path. Yeah. Okay. Jerry. We can separate read memory and write memory. We always separate read memory and write memory from each other. Yes, and then there will be some challenges actually. You are on the right track. So for example, if you want to read the temporary data, what should we do? And we're going to talk about that. So there will be a queue that we're going to read from that queue instead of reading from the actual memory. We're going to talk about that as well. Any other questions? Yes. So the question is, when we are actually executing, why don't we check whether this is going to be flushed or not? They're going to be, so there are many instructions that potentially can be flushed. So essentially, any instructions after a branch could be flushed. But now I have a choice, whether I say that, oh, I don't execute this because they might be flushed. But remember, the whole point of execution is that I want to search and be able to execute more. So I'm going to speculate and say that, okay, this is not going to be flushed. Let's execute this. If it's going to be flushed, I have a mechanism for recovery. So same story that we tell for branch prediction, that if we reach to a branch, we either can stall the processor and say, okay, let's not do anything until we make sure. That's one strategy, but that would be a very slow strategy. The alternative strategy that we do is the speculation, which means that let's assume that this is going to be used. Let's actually execute them. We will have a mechanism to figure it out later. Okay? That's why we will have what we call retire. Retire also sometimes called commit. So if you see in some references that says commit and retire is the same concept. In this class, we're going to do complete and retire. There are some other notations that people use. Just keep in mind that commit and retire is the same thing. Okay, so back to the question that originally one of the classmates asked, that what does it mean for instruction to complete and what does it mean for instruction to retire, okay? So when we see that when the instruction is like done, okay, when we finish an instruction, we usually, write back the data somewhere, right? So we either write back the data to the register file, right? Or write it back to the memory, or write it or update it the PC. These are the three places that we write back, okay? And then if we are already writing to these kind of permanent storage places, then it's impossible for things to recover because we're not going to know what we wrote and what was the previous data, because this one's going to overwrite the previous data. So we won't do this. Instead, we're going to write it to some temporary buffer. And when we are absolutely sure that this can be written to these permanent storage systems, then we're going to write it to those, okay? So as I said, what we're going to do is that this basic idea that we're going to let the instructions to complete out of order, but we're going to only retire instructions in order, okay? And then if you remember the register file, memory, and PC, these were what we call architectural states. So the difference between retire and complete is that complete writes into your microarchitectural states, but then retire going to write into your architectural states, which means that my register is now updated, my memory is now updated, my PC is now updated. So anything that software can understand happens after retirement. the software will not know which instruction has been completed when. So this is completely within the hood of the microarchitecture. Okay? And then why this would work, let's actually revisit this example here. As you can see, now I have this. And now I have completed instructions. Now all of these instructions are in that temporary buffer. Okay? So what I can do now is that I have a separate one called retire. So I have a separate buffer called retire. And here's what I'm going to do. I'm basically going to say that I can only move instructions from complete to retire when all the prior instructions to that instructions are already completed. So I1 can be retired because there is nothing prior to I1 in this design. Now, since I retired I1, now I2 can also be retired because I1 is already retired. So I can also retire I2. So I can get rid of I1 and I2. But now, can I retire I7 or not? The answer is no, because I need to wait for 3 to 6 to be completed first. Once they are completed, then I can retire. So I7 stays in this complete until these instructions are going all to the complete. And now what happens? Now if I want to flush this, not only I flush the pipeline, I will also flush my complete. Okay? So I flush all these things, and then next time I'm gonna run I4, and let's say, for example, I'm going to jump to I8, so I'm going to continue I4. So as you can see, the things that have been retired are I1 and I2. There's also I3 that I need to run, so I basically need to kind of complete the I3 as well. There's a potential way of not flushing I3 at all here, which I'm going to describe later. But at some point, I3 will be also show up in this complete, and they're going to be retired, and so on and so forth. Okay? So here's how we make the difference between retire and complete. Things in complete will be also flushed from the pipeline. Things in retire not going to be flushed from the pipeline. Yes? Mm-hmm. So the question is, how do we know that what is prior instructions, right? So that's the question, right? How do we know the age of an instructions? We're going to use PC for that. So essentially, we're going to say anything that PC is prior to that, these are older instructions. Anything beyond PC will be newer instructions. So we're going to use PC, and we're going to have a pointer. So something like a stack pointer that we're going to point to the top of the last instructions that have been retired. And then we're going to use that. I'm going to show you the actual detail. Yes? Yes, so the question is, in this example, let's say, for example, I4 was a branch that indeed was not taken. What would happen in that case would have been that at some point, I4 will go here, I5 will go here, I6 will go here, and then we're going to retire 3, 4, 5, 6. And since now we retired 6, now we can go back and retire 7. So 7 has to wait for a long time in that queue. But if the queue is long enough, that's totally fine. Mm-hmm. Yes. That's also a great question. Since I8 haven't seen prior instructions, what should we do? And again, we're going to talk about how do we update our ROB to keep track of that. Mm-hmm. So the question is, can we retire things if we don't know, if the prior instructions are all safe? You don't do this because there are many, many reasons that instruction could be flushed. So for example, there will be exceptions, there will be interrupts, there will be system calls. So there are many reasons that instructions can be retired. So typically, we just follow this very strict policy that we're not going to retire things unless prior instructions are all retired. Mm-hmm. Yes. Good question. So do we now forward from complete to execution? Exactly. Yes. Mm-hmm. And we're going to talk about that. Yes. Jerry? Well, every instruction goes to the reorder buffer. There's no difference. Yeah, the question was about branch instructions. So all the instructions goes to the reorder buffer. Yeah. Mm-hmm. So the question is, how do we know that, for example, if we jump back, then we're gonna have the circular problem? I'm gonna show you how we actually create this reorder buffer, and you will see how the other question that someone asked is like, if I8 is going to be inside the complete, but we never saw I7, how do we even know? We're gonna show you how we fix that problem. Mm-hmm. Okay, so how do we implement this? And then that's kind of, will also answer some of your question, is that we're gonna use a buffer, a temporary storage unit, which you can think about as something similar to your register file, that's gonna store this temporary data, okay? Um, so this is what we call reorder buffer, or ROB, okay? Reorder buffer is the circular buffer. The reason it's circular is that we want to kind of like reuse, because things goes into the buffer and then they're gonna push out of the buffer. So at some point you want to go back and reuse them, okay? And it holds all what we call the completed instructions, okay? So any instruction that is completed, it's written into that ROB, into one row of that ROB. Think about an ROB as a table with multiple rows, let's say 8 rows. Usually in like modern systems like 128 or 256. So it will be a system like a table like this, that each row belongs to one instruction. So you write it here, and then you move to the next one, you write it here. At some point, for example, say that, okay, this instruction can be completed. And as I said, this is a circular buffer, which means that at some point that we reach to the end, we go back up, and we're gonna replace things, okay? And the criteria for retiring an instruction is that we're gonna retire an instruction only if that for any IX, instruction IX, all IJ such as J is less than X is already retired, okay? That would be the criteria for us to retire instructions, okay? So here's kind of like the updated figure. So as I said, on my front end is in order. I'm gonna have a buffer here. I'm gonna describe that later. Then I'm gonna execute things out of order. Then I'm gonna have a complete stage. And then I'm gonna write things into the reorder buffer. As you can see, not necessarily all the instructions are already filled in. And I'm gonna then push things out of my retirement based on this criteria that I described to you, okay? How do we keep track of what was the last instructions that we got rid of? We're gonna have a pointer called head of the ROB, okay? So the head of the ROB always points to the latest instructions that can be retired, okay? So at the beginning, we always point to the first instruction, I1, okay? So the way it works is that we're gonna, at some point, I1 will come, and when the I1 comes and it's head of the ROB, I can retire. So in the next cycle, I'm going to retire I1, and I'm going to push down my head of the ROB to one more instructions, okay? So in this case, this. So now, since everything else is behind the head of the ROB, none of them can be retired, okay? All of them has to wait. Then what happens is that at some point, I2 will arrive. So as I said, I3 and all this subsequent instructions cannot be retired at this point until I2 arrives, okay? At some point, I2 will arrive, and since I2 is the head of ROB, then we can retire instructions, okay? So I can definitely retire I2. Now the question is, how many can I retire? Can I retire all of them? Can I retire 2 of them? Can I retire 4 of them? That's the design of your processors. In most processors, the number of instructions that we can fetch is the same number that we can retire, okay? So this is why we usually call them, this is a 2-issue processor, or 4-issue processor, or 8-issue processors. The reason that we have limited number of things that we can retire is that, remember, retiring requires writing back, for example, to your register file. If I want to write back to the register file, I need to have ports, right? So for example, if I only have 2 ports that can write to the register file, I can at most write 2 instructions to the register file. So I can only retire 2. So there is a limit to how many I can do. And of course, I want to be able to retire fast, because retiring fast means that this table can be smaller. So it helps. But there is a trade-off. If I can retire more, it means that I need more pins, I need more ports. So there's more also kind of overhead in my hardware design. So typically we have like 2 or 4 or some number like that. This is just a design choice in your system, okay? But keep in mind that I cannot retire all. So if I have, let's say, I3, I4, I5, I6, like all of them ready, and my processor can only retire 2, at any given point I retire 2 of these, I push the head of the ROB here. In the next cycle, I'm going to retire the next 2. And then in the next cycle, I'm going to retire. Hopefully, the design is kind of like nicely balanced, which means that I completed 2, I retired 2, I completed 2, retired 2. That's how I'm going to get the IPC equal to 2, right? Yes? Yeah, so the question is, can the ROB get full? And the answer is yes. The ROB can get full. Usually, ROB is big enough so that it's not become a bottleneck. But for example, think about like an instruction that's taking a very, very long time, and it's head of the ROB. And then we push a lot of other things into your ROB, okay? So your ROB can get full. And if it gets full, then it's what we call a structural hazard, like before. We need to stall the process. We can no longer fetch things until that instruction arrives. Yes? It's circular. So ROB is circular so that we can actually reuse rows. Yes. Great. So, and then as I said, the nice thing about flushing is that if for any reason, for example, if I2 was a branch instruction, and we realize that I2 is misprediction, for example, and I need to flush things, all I need to do is that I go to my ROB, I look at the head of the ROB, I'm going to say everything beyond that, bye, right? So we flush everything outside my ROB beyond that point. Everything before, they are safe and they're good. Everything after, we have to get rid of all of them, okay? So it's wasted cycle, but we can recover very easily. So nothing bad happens, because all you need to do is basically just invalidating all these components and contents here, okay? So how does the ROB look like? It looks like something like this. Actually, later in the lecture, I'm going to show you an example. Keep in mind that different microarchitectures have different things. So this is not like a standard. If you remember, I told you that you can design microarchitecture differently, and there are different versions. But typically, you want to store different things, such as, for example, you want to store PC. If this is memory, for example, you want to store the address and the data that you want to store in the memory. You want to store the destination register value. You want to store what is the destination register. You want to store whether this line is valid or not, and those things. And there could be many other things that we can use. We're going to give you a more concrete example later in the lecture, but keep in mind that modern systems, they might have many different entries. You can actually search and see what are the entries for an ROB, okay? So if I want to update my kind of data pattern controller, this is where the ROB will sit, okay? The ROB kind of will sit, and we're going to replace these lines that we had for the register file and for memory, okay? Now I have this kind of purple-ish lines that now I'm connecting this to this, and connecting this to this. I'm connecting this line to here. And I'm no longer connecting register file. Instead, I'm connecting my ROB to register file, okay? And as you can see, ROB also reads the instructions so that to create a new entry into the ROB, okay? So this is how we're going to change the design. So everything from the execution units goes directly to ROB. From the ROB goes to the register file, okay? This kind of ROB becomes the gatekeeper for the memory and for my register file, okay? And then this was the data path without ROB, obviously. All right, So if you remember, I told you that there are three things that I need to fix. The first thing was a mechanism for recovery. And this is what we discussed so far. So essentially, any sort of speculation, branch misprediction, and all that can be fixed this way, okay? So let's talk about these other two problems. I'm going to talk about this one next. So how do we fix data hazards in this particular case? Are there new data hazards, and how we fix them? Let's have like a 2-3 minutes break, and then I'm going to talk about this, okay? Seems that I'm recording, which is great. And 1, 2, 3. Okay. All right. So let's talk about this second problem. Okay. And if you remember, I talked about this and I told you that some of these dependencies are not real dependencies in order. But I also told you that when we go to out of order, these are going to be a problem. So let's revisit them. So we had this old classic problem of read raw data hazard. So for example, we had add x2, x1, x3, and then at some point we're going to read x2. And if you remember, we said that this is a problem. We call this raw data hazard. We fix it by forwarding or stalling the processors. Now let's see what will happen if I actually reorder these instructions, because now this is also an option. So if I actually run this prior to this, I'm going to still have the issue, because in program order, I'm expecting that x2 is updated first and then read next, okay? So if I run this out of order, I'm going to run into issues, because at this point, I'm going to read this first, and then later on, I'm going to write to it, and this is not what we want. So I need to be very careful about this. This is what we call true dependence. This is still a raw data hazard. It was existed in my pipeline design, still exists in my out of order. So I have to be very careful about this. I should prevent such things from happening. I'm going to later show how we're going to do that, okay? So raw data hazard exists, and we have to fix it, okay? But let's talk about others. So this is true, and it still exists. But let's talk about the other options. For example, let's talk about write after write, or WAW. This is what we call output dependence. If you remember, it said that in order processing, this is not an issue. So by the way, this is the scenario where you write to x2. Later on, some instructions later, you again write to x2, okay? In order, this was not an issue, because we said that we always make sure that these things happens in order. But in out of order execution, if I run this prior to this, then we're going to run into problems, okay? Because now I update this value based on this sub, and then later on I'm going to update it based on this x. So at this point, the value that I'm going to see is the values coming from the add, versus in the original instruction, the value I was supposed to see was the value that's coming from the sub, okay? So that will be an issue that we need to fix in our design. And again, remember that this is different from like the flashing and all issues. This is when we are completing things out of order that we're going to have this issue. So we have to be very careful about this as well, okay? And the last thing that could also happen is what we call write after read. This is what we call anti-dependence. And again, it's a scenario where we read first and write next. In order, this was not an issue, but if you look at the out of order, you will see that if I write first and then read next, I'm going to read an incorrect value. So this is going to be a big problem as well if we run this out of order. So we have to be careful, okay? So long story short, we're going to have all these three problems in out of order, because we're changing the order, and changing the order could cause issues. In order processing, we only had this problem. And still, we're going to have read after read that it's not going to be a problem in any case, because it doesn't matter when you read. We can read multiple times, okay? So 3 out of 4 is going to be an issue, okay? But here's the idea that we're gonna do to fix at least these two. So for the first one, there is a longer solution that we're gonna discuss later. But for these two, there is an easy solution. And that easy solution is this: that if any of these two was a separate register, for example, if this x2 was x5, okay, then it won't matter which order I'm going to use, right? As since I'm just using I'm overwriting a register, I'm using separate register. If this was x5, then if this was x5, for example, then I can reorder them as I wish, right? So, for example, add x2, x1, x3, and sub x5, x3, x4. Are you okay? Okay. And then if I just reorder them sub and then add, you will see that it doesn't matter which order we're gonna do. Let's pause for a sec. Right? So the idea of the kind of the solutions that we're gonna go after is that if we can quote unquote rename the registers, then we kind of get rid of this output dependence and anti-dependence, because these are supposed to be different registers anyway. We just made a mistake we made a bad decision of using the same registers. If I'm going to overwrite these registers, doesn't matter whether they're same registers or different registers, okay? So if I can do this, if I can rename my registers, then I can run them in any order that I want, okay? Same story for write after read. If I change this, then I can just read them in any order that I want. It's not going to fix this issue because these two registers are dependent to each other. But remember that these two registers are not dependent to each other. And same for this one, okay? So this is what we're going to do. So essentially, we're going to rename registers for false dependencies, because right after read and right after write, they're not true dependencies. They're false dependency, which means that there are supposed to be two separate registers. So let's actually use two separate registers. For raw data hazards, we need to do something else. I'm going to discuss that later, okay? So this is what we're going to do for our out-of-order processor. We're going to do this additional step during our decode called register renaming, okay? We're going to rename registers in order to fix this issue of dependencies, of false dependencies, okay? And here's the additional things that we're going to do. So remember when we were designing the ISA, I told you that RISC-V has 32 registers, okay? We call that 32 registers architectural registers, okay, or AREG, all right? But in reality, you might wonder that why are we only using 32? Why don't we use 128 or 256? I can have bigger hardware, I can have bigger register file, okay? But if I want to stick to my ISA, doesn't matter how many registers I have. I only can address them as x1, x2, x3, x4. So I never can have x63 or x121, because in my ISA, I cannot show it. I only have 5 bits in my ISA, in my binary machine code. So I can never do that. But if I now can rename registers, why don't I actually rename registers to these other numbers, okay? So I read the registers that is like x5, but then I can map it to whatever registers that I want, okay? So this is the idea of what we call architectural registers versus physical registers. Physical registers are actual registers that we have in our design. It could be much, much more than the 32 that we have in RISC-V. But my architectural registers are basically frozen and limited to my ISA. For example, for RISC-V, we only have 32. We never can increase that number, okay? But we're going to have PREG, physical registers that could be multiple. So what will happen is that we're going to have scenarios where one AREG has been mapped to multiple PREG. But since these are different instructions, we're going to hold different copies of my data. So how do we keep track of this mapping? We're going to have this thing called register alias mapping table, or RAT, okay? So what RAT does is, I think about this as a table where we have one entry per AREG. So we have 32 rows in this RAT, and we're going to store different mappings. So maybe let's say we have 4 columns or 5 columns or whatever. We can map one architectural registers to multiple physical registers, okay? And then essentially each row shows you all the possible mapping of that table, okay? So here's what we're going to do. We're going to use this table called RAD, and we're going to map these architectural registers to some physical registers. How do we know which physical register should we use? We're going to have a separate table called free pool, okay? That we keep track of all the available physical registers here, and we're going to just pick one randomly from here and assign it to the array, okay? Let me give you a running examples, a concrete examples, and go through the algorithm of the renaming. Then you will understand what we're doing, and then we're going to revisit why we are doing this, okay? So let's, for example, for now, let's start with something simpler. Let's say we have only 5 architectural registers. Let's say we only want to map x1 to x5, okay? And let's say we have only 10 physical registers for now, okay? In reality, as I said, we have 32 architectural registers, and we have usually 128 or 256 physical registers. For this particular example, let's do 5 and 10, okay? So we're going to have 2 tables. And remember, these are all happening during the decode stage, okay? So what I want to do, I want to rename my architecture register and assign a physical registers to each one. So let's see how we do it, okay? So we're going to have a table called register alias table RAD. I'm going to have a free pool, all right? So I'm going to start with some initial mapping, okay? So we're going to usually start when the system boots up, we're going to do some mapping. Let's say, for example, I map x1 to p1, I map x2 with p2, x3 with p3, x4 with p4, and x5 with p5, okay? And by the way, the notation we're going to use for physical registers is with p, okay? So this is how we distinguish between architectural registers, which we use to show with x, and now physical registers, so we show with p. Okay, if I do this initial mapping, remember that I had 10 registers, which means that now I have 5 more registers that are not assigned to anything. In other words, they are free. Okay, so I put them in my free pool. Okay, now let's see how we do. So let's say, for example, I have these 4 instructions that I want to decode. Okay, so I have OR and add and a sub and an add-I, and I want to decode this. Essentially, I want to map these registers to this physical registers, okay? So that's how we do it. So let's start with the first instruction. So here's the algorithm that we're going to use, okay? So if you remember, each instruction had some source registers and some destination registers. In some cases, we only had source registers. In some cases, we had 1 source register and 1 destination registers. In some other cases, we had 2 source registers and 1 destination, okay? The algorithm that we're going to follow is as follows, okay? So we're going to look first at my source registers. In this case, I have x1 and x2, okay? So what I'm going to do is that, so I'm going to say OR, okay? So I'm going to look at the x1 and say that, okay, I'm going to go and look at my RAD and see what x1 has been mapped to, okay? So x1 has been mapped to p1, so I'm going to put p1 here. Then I'm going to look at x2 and see what x2 has been mapped to and see p2, so I'm going to put p2 here. And now the question is, how do I map the destination register? One option is that I'm going to map destination register to P3, and I'm going to put P3 here. The problem with this approach is that, remember, I want to get rid of output dependency. So what I want to do is that for every new destination register, for every new register that I want to save the data to, it's better to use a new physical register. So this way, I'm going to decouple the source registers, the destination registers from each other, okay? So instead of using P3, I'm going to assign a new register to this. So I'm going to go through my free pool and say, okay, P6, the first register that is available, I'm going to assign P6 here, okay? And what I'm going to do is that now I'm going to update this to X3 is now mapped to P6, okay? And there is also, we're going to, for some reason that I'm going to describe later, I'm going to also keep, remember what was the last mapping that I used for these registers. This is used for when we need to flush things and we need to recover to the previous one. Later, I'm going to describe why we need this, okay? So I'm going to update this line using this format, okay? So let's continue. So So now I'm going to do this for the add, and I'm going to repeat the process one more time, okay? So for add, so this is, by the way, this is the new mapping. And as you can see, the P6 no longer exists in my free pool because it's no longer free, okay? So I'm going to go to add, and I have X3 and X4, okay? So I'm going to put add. I'm start with the first source register, X4. I'm going to see X4 is mapped to P4, okay? So I'm going to P4 here. Now I'm going to see X3, and remember, X3 here is the new mapping now. So I'm going to put P6 here, okay? And now I have X4 here, which is the destination register. And as I said, I'm going to use a new register. So I'm going to change P4. I'm going to pick P7, put P7 here, and I'm going to put P7 here. Okay. So again, whenever I have a destination register, I want to use a new physical register. The reason for this is that I want to decouple registers from each other such that they no longer have output dependence in my design. Okay. But as you can see, this X3 and this X3 are the same, and you will see that this P6 and this P6 is also the same, okay? But for example, this X3 and this X3 are the same, but since these two are output dependent, you will later see that the sub, this X3 will be mapped to P8 this time. So we're gonna have P8 and P6. This used to be X3, but now they're two separate physical registers, okay? Yes?
The very first instance of X3 in the first time, why do we just not use X? Why don't we just not use P?
Good question. The question is like for the very first instance, why are we not using this? Yes, you can. So essentially, I'm showing you a snapshot. So there's not like they're never a very first instance, right? Like you always like running and there is some prior mapping. Yeah, so in like very first instance, there was nothing here. If there was nothing here, then you pick P3 out of the free pool and put it there, right? So, but what I'm showing you here is that there's always a previous one that's been mapped to. That's why we always change it. All right. So continuing on, as I said, so for add, we're gonna take X3 and X4 using P6 and P4. For X4, since this is a destination, we're gonna pick a new register. We're gonna get rid of P7 from the free pool. We're gonna replace P4 with P7, and we're gonna continue. As you can see, this is P4, but this is P7. This is X4, but this is the source register. This is the destination register. That's why there are two different physical registers, okay? That's how we are actually using our physical registers. So let's continue. Let's think about this one. I'm going to give you 1 minute for you to actually do this yourself, and then I'm gonna do it myself. All right. So we have a sub. As I said, we start with these two sources. X2, we're going to go and see what is there. It's going to be P2. Then I'm going to look at X5, and I'm going to see that it's P5. And then this is my destination register X3. We need to assign a new registers to this. We're going to go to my free pool, pick the first one. And in this case, it would be P8. I'm going to put P8. And I'm going to also update this, and I'm going to put P8 here. Okay? And as I said, as you can see, the big difference, the whole thing that this will buy for us is that we're going to get rid of this output dependence. As you can see, in this case, we couldn't reorder sub and or because this was the dependency. But now I'm free to reorder these guys. There's no problem with reordering these two instructions. Okay? Because there are two separate registers that they're using, so I can reorder them as I wish, okay? So this will help us later to reduce the dependency. So I'm gonna use more physical registers at my disposal to reduce the possible overlap. I'm not gonna be able to remove all the possible overlaps, but I'm gonna significantly reduce the number of overlaps, okay? And then finally, let's do, any questions here? Yes. So the question is that is P3 and P4 are now free, And this is a good question. I'm going to later say how do we going to free. No, it's not free yet. We're going to only free when they are retiring. So we only retire. When they're retired, we're going to free, put them back into the free pool. All right, so last instruction, add I. So this add I, as you can see, for example, this is an immediate. There's nothing you want to do for an immediate. There's no renaming needed for immediates. So you just put the immediates here. X3 now is P8. And then X1 needs to be mapped to P9, okay? So add I. And you might wonder that what will happen if there is no free pool, like free registers. If there is no free registers, you have to stall, but this almost never happens because you have many, many registers, many, many more registers compared to architecture registers. So things will be freed at some point. I'm going to talk about it later. So things will come back here. So for example, P3 and P2 and those things going to come back here. And as a result, I can reassign them to the free next instruction. But for any reason, if there is no instructions in the free, no registers available in free pool, we have to stall, which means that I can no longer decode more instructions. I have to wait for for registers to become free, and then I can continue. Okay? All right, so now the question of when do we free? And when we do free is when the instruction retires, okay? We're gonna free the old destination register, not the current destination registers, the old one. Why we need to do that? So essentially, if you look into this, if you remember, originally X3 was mapped to P3, and I told you that I'm gonna do P1, P2, and then P6, which means that I'm gonna replace P3 with P6, okay? I'm gonna save this in my RAT and in my ROB. When this instructions gets to the retire stage, okay, what I'm going to free is P3, not P6. Why? Because P6 is still so P6 is a new destination register. And if you pay attention, you will see that P6 is going to be used in future instructions, okay? When I want to get rid of things, I get rid of because when this instruction is safe, okay, it means that this value can be stored permanently, which means that I no longer need to remember no longer need to recover this instruction, okay? And the old destination register was stored because if we want to recover, we want to go back to that old destination register, okay? So when this instruction is safe, means that I no longer need to remember what was the previous mapping for that particular register. But for example, for this, we might still need to remember the prior mapping. That's why I don't free P6, I free the older one, P3, okay? So again, if I have something like this, I keep track of the old one because if for any reason I decided that I need to get rid of this, I need to revert back my RAT to X3 P3 because if this instruction never happens, my RAT should have been X3 and P3, right? Because this was the original mapping between the two, okay? So if this instruction has to be flushed, I need to remember what was the last thing that I used. In this case, it was P3, so I would recover my RAT to P3. But now that this instruction is retired, now it's safe to get rid of that memory, okay? So now we know no longer we need to recover this instruction. As a result, we no longer remember P3, so P3 will be going back to my free pool. P6, whether or not we can free P6 doesn't matter here because this is not the mapping for P6. P6 at some point later was mapped and replaced by something else. At that point, we're going to release P6, okay? So these are the difference. So we kind of the reason for this is we want to keep track of the previous mapping of the RAT, okay? So how do we actually put the RAT? So we're going to put the RAT into our pipeline this way. So essentially, when the instructions are fetched, we're going to put them into the RAT first. And from the RAT, we're going to put it into the physical registers. And as you can see, now my register file is physical register file. So these are actual P0 to P whatever. It could be P 127 or something. So here is still I have X1, but from here to here now I have P1, P2, and so on. Okay, and from here on everything is physical. Okay, so everything is based on the physical registers. And what will happen is that my ROB now needs to tell the rat that you can free things, okay? So when we retire, we're gonna also inform rat that, oh, I retired this instruction. Here, this was the old register. Now go and put that old register back into your, to your free pool, okay? And if I want to flush things, what I need to do is that I will tell rats that, oh, these instructions are flushed. So whatever you did, revert them, right? Recover your previous mapping. Because if these instructions were flush, not only you have to get rid of them from the ROB, you also have to fix the things that you've changed along the way, including your rat. Okay? Questions? Great. So I talked about this, I talked about this. Let's talk about the last thing about out-of-order execution, okay? So I need a mechanism to figure out what is ready and what is not ready. And I already told you that, for example, if there is dependency between the registers, if there is a branch and all that, we need to take care of these things. So this is kind of like the main part that enable us to do out-of-order execution, okay? So far we talked about ROB and we talked about RAT and physical registers, in other words, renaming. The last thing I want to talk about is what we call scheduling or reservation stations, okay? So the idea that we are going after is this, that let's say, for example, I have a sequence like this, that I have add x3, x2, x1, I have sub x4, x2, x1, I have add x6, x4, x3, and then I have add x7, x0, 10, okay? As you can see, for example, here, there is some form of a dependency between this guy and this guy, okay? But, for example, this instruction is completely independent from these other instructions, okay? So I can freely run these instructions in any order that I want without being worried about the dependency. But I cannot, for example, run this instruction prior to this instruction. And again, remember, renaming is not going to help here as well, because renaming is not going to fix the raw data hazard that you had before, okay? So I need a mechanism to know who is ready and who is not. And then those that are ready, I need a mechanism to select them and let them to be executed. In other words, what we call issue them, okay? This is what we do in part of what we call scheduling, okay? So how do we schedule? We're going to do and use this buffer called reservation station, or RS, okay? This reservation station is basically sits right after the decode stage. And what it does is that instructions that you kind of rename and read the register file, you're going to go and store them into this reservation station, okay? And then from this reservation station, then what I can do is that if I have a mechanism to kind of keep track of who's ready and who's not ready, then I can basically pick the instructions that are ready and execute them. Those that are not ready, they will wait. Once those that are ready are going to execute it, hopefully at some point, they're going to update this reservation station. And those that were not ready now become ready. So for example, going back to this example here, for example, x3 needs to wait for x1. So x1 is ready, x2 is ready, x4 is ready. Maybe all three can be executed. At some point, x1 going to be completed. So from x1, if I forward the value or if somehow update the values, now I3 also becomes ready, right? So this is the mechanism that we're going to do. We're going to read these instructions in order, fetch them 2 by 2 or 4 by 4 or whatever number that we have, put them into, rename them, put them into the reservation station. In reservation station, we're going to keep track of their operands. If we see that all the operands are available and ready, we're going to execute them. We're going to write them into the ROB. We're going to update our reservation station, and we're going to recheck our reservation station. If there is something that we can issue again, we're going to issue those instructions, okay? This is the story of how do we schedule things. Um, and, and then, as I said, the execution can happen out of order, okay? So how do we actually design our execution? We design our execution the same way that we had before. Remember, we had one ALU, but I told you that for superscalar, we can have multiple ALUs. This is what we have, right? So we have fetch and decode, but my execution can now be multiple lanes, okay? Another option that it can have is that I can also pipeline my execution state. So in the past, it was just one cycle. But if, for example, I have multiple different operations. Let's say, for example, I have floating point operations versus integer operations. The integer operations are very quick, and it happens in one cycle. Instead of waiting for the floating point to finish and then do everything in one cycle, I can also pipeline my execution stage. So I can have multiple lanes, and these are different ALUs. And within each lane, I can also pipeline them, okay? Whenever they finish, they're going to write their data back to the ROB. Okay, so this is the point that they're completed. And then from the ROB, we know the story. We can kind of retire them and all those things, okay? So essentially, in superscalar processors, we're not going to have just one ALU. We're going to have multiple ALUs. We call them functional units, or FU. Very interesting name. And we're going to pipeline these FUs, okay? So we have multiple FUs for you, and they are pipeline, okay? And then you can think about this different operations. Some of them could be for the memory, some of them could be for integer operations, some of them could be floating points, some of them could be reused for all of them, and so on and so forth, okay? So as I said, for example, I can have integer add, I can have integer multiply, I can have floating point multiply, I can have load the stores. I can even treat my load stores as a functional unit, because reading from memory is also an operation, right? So I can treat them as a functional unit as well, okay? So as you can see, basically the idea would be this, that I fetch, the decode, I rename, I put them into reservation station, and when they put them into the execution stage, we call it issue, okay? I'm issuing this instruction. The instruction goes through the pipeline stages of my execution. Simply could be just one stage as before, like for example, an add. Once it's done, it will be completed and written into the ROB. At some point, it's going to be retired from ROB and be written back to my register file and all that, okay? So that would be basically the timeline of an out-of-order execution system, all right? So again, this would be basically the updated version. So I'm going to have fetch, decode, rename, reservation station, execution, retire in order, okay? How does the reservation station look like? Reservation station is looking very similar to my ROB. I have each row, one row for one instructions. Within the row, I have multiple columns. So for example, I have the operation, I have the destination registers, I have source register 1, source register 2, the immediate, the ROB that this one is pointing at, the functional units that we're going to use, and so on. The very, very important things are these two guys, source 1 ready and source 2 ready. The way that we're going to decide whether or not this instruction is ready to go is that if both of these numbers are equal to 1, okay? This is how the simplest way that we can decide whether an instruction is independent than the previous instruction is basically these 2 bits. So essentially what we're going to do is that when we're going to put the instructions into the reservation station, we're going to check whether or not this source register 1 or source register 2 is dependent to any previous instructions. If it is, we're going to put source ready equal to 0. If it's not, we're going to put source ready equal to 1, okay? And the way that we're going to decide which instruction is ready or not is that we're going to go through instructions one by one. Think about this as kind of a for loop. We're going to go through the instructions one by one and check these 2 bits. If they are both 1, then this instruction is good to go. We're going to issue it into our execution state, okay? And of course, if you have, for example, something like add I that has 1 register and 1 immediate, then one of the resources are always ready, right? So the immediate one is always ready. So you put 1 there. And the other one depends on whether the register is dependent on something or not, okay? So here's the steps for execution. The name's kind of similar or we usually use a different naming. Some of them are exactly the same as we had in our five-stage pipeline. Some of them are slightly different. So we have our fetch, and remember our fetch now, there are multiple instructions being fetched at the same time. For example, if you have a 2-issue pipeline, we fetch 2 instructions. If our 4-issue, we fetch 4. We fetch in order, which means that we fetch PC and PC plus 4 and maybe PC plus 8 and so on and so forth. Then we go to the dispatch unit. The dispatch unit is basically where we're going to, after fetch, we go to the decode stage, and from decode, we go to the dispatch unit. Decode is the same as what we had before. And during the dispatch unit, we're going to put things into my reservation station. This means that I'm going to copy the values. I'm going to read the values from the register file and copy it into my reservation station. I'm going to also reserve a unit in my ROB. Okay, that's a very important part of a dispatch. And then if either RS, reservation station, or ROB is full, we're going to stall the processor. We're going to stall the fetching and decoding. We're no longer going to decode and fetch until one entry becomes available. Okay. Once we put things in the dispatch, then the next cycle would be issuing, or in some cases they call it fire. We're going to call it issue in this case in our class, but some other books call it fire. So essentially, firing or issuing based on whether or not I have an instruction that both of their operands are ready, and I have an available functional unit. Okay, so I need 2 things. I need an available functional unit. I also need an instruction that has at least 2 available operands or source. Okay. Once we do that, we're going to issue the instruction and put it into the execution unit. That means that I can now release them from the reservation station. I no longer need to save them in the reservation station. So I'm going to let the reservation station go. But remember, I'm going to keep the ROB. Okay? And then I'm going to have the complete. Complete is when the results of the execution state is copied into and written into the ROB. But we're not going to let go from ROB. They're going to stay in ROB. And at some point, we're going to have the commit or retire, which means that that instruction has reached to the top or head of the ROB, which means that now I can write this back into my register file or my memory, which means that I also can release the old destination register and put it back into the free pool. Okay? So these are the steps that we're going to do. All right? So let's actually do this one kind of giant example together. The TA will also do another one. And this is typically what we're going to ask you in a quiz as well, that you should be able to do this. Okay? So let's go through this 4 instructions. And we're going to do everything, starting from fetch all the way to retire. And here you see a bunch of different tables. Okay? So this one is my ROB. This one is my reservation station. This is my functional unit scoreboard. This is basically keep track of how many functional units that I have and whether or not they're available. This is my RAD, this is my free pool, and this is my scoreboard for my registers, basically saying that which register is ready and which register is not ready. And remember, we still have just 5 architectural registers, and I have 10 physical registers, okay? And here's the components that I have in my ROB. I have a valid bit that initially all of them are 0. If it's 0, it means that they're not valid. I have the destination register. I have the old destination registers. I have the PC, and I have whether or not this instruction is complete. And this kind of arrow here is the head of the ROB. So at the beginning is at the top of my table. Okay? In my reservation station, I have this use, which means that, again, this is valid or not. I have the opcode, which kind of keep track of the opcode. I have my destination register, source register, immediate. Also have immediate source register 1 ready or not. This is a 1-bit flag. And then I have the functional unit. This is the functional unit that we're going to use. Okay, so for example, functional unit 0, 1, or 2. And this is the pointer to the ROB. Remember, when we are putting things in the reservation station, we also need to reserve a line in ROB because these two needs to be linked together. Otherwise, we don't know which instruction belongs to which ROB, okay? So we're gonna do that too. And functional unit, this is usually called scoreboard. This is basically just keep track of functional units. For example, as I said, functional units could be dedicated to a particular operation or could be generic. Let's say, for example, I have ALU1 and ALU2, which means that they can do generic ALU operations. Let's say ALU2 can also do multiplication. In class, we didn't go over multiplication, but let's assume that multiplication is just another R-type instructions for simplicity. And let's say we also have a functional unit for memory, which is a queue that we're going to store things into the memory, okay? And this yes or no means that whether they are available or not. By default, they're available. If we schedule something, they become unavailable until the cycle that become available, okay? RAT, you already know, X1 and P1, X2 and P2, and these are the initial mapping. And lastly, we have a scoreboard for my register file. This basically tells you whether or not your register file, those registers are ready or not. By default, everyone is ready unless they go to the execution stage and then become not ready. I'm going to talk about that, okay? So let's talk about these 4 instructions. Let's say I have a load word x2 0x1 stored in address 0x100. Then I have add x4 x3 x2. Then I have OR x5 x5 and x4. And let's say I have another load x4 0 x5 x4. And let's say I have a 2-issue processor, which means that I fetch 2 instructions per cycle, okay? So here's how I'm going to do this. So I'm going to show you the cycle and then show you the operation. Since multiple operations happen in one cycle, you're going to see this multiple things. Per slide, I'm going to show you just one operation, but keep in mind that everything in C0 happens at the same time, everything in C1 happens at the same time, and so on and so forth, okay? So let's see what happens. Any questions so far? Great. So in cycle 0, I'm going to fetch 2 instructions. So the fetching is like before. So I'm going to do the PC. I'm going to fetch this instruction, read it from the instruction memory. I'm going to also fetch PC plus 4 and fetch this one, okay? The fetch cycle is straightforward. There's nothing unique. The only difference is that I'm fetching 2 instructions now, okay? Now I go to cycle 1. There's nothing else that I do in cycle 0. In cycle 1, I need to decode. And again, I need to decode 2 instructions. Decoding is the same as before. There is a controller. These instructions go to the controller. We check the opcode. There's a whole bunch of things that you need to assign. I'll do that, and great. In the same cycle, I also need to fetch the next 2 instructions, right? So I'm going to update my PC from here to here. I'm going to fetch these next 2 instructions in cycle 1 as well, okay? So again, that's it. So now I go to cycle 2, and these are when new things are happening. So compared to in order, for in order at this point, the first 2 instructions would have gone to execution state. But in out of order now, you first need to rename them. Then I need to dispatch them. Then I will execute them, okay? So there are 2 middle steps that I need to do. So how was the renaming work? If you remember, so renaming was that I take the source registers and I look at my RAT and replace them. So in this case, X1 is my source register. I go to my table and see that X1 was mapped to P1. So I'm going to put P1 here. 0 is the immediates. There is nothing we can do about this. We don't need to do anything for them. And then X2 is my destination register. For load, remember that we read data from the memory and write it to the registers. So in this case, X2 becomes the destination register. And if you remember, we need to change the old mapping, which used to be X2 P2 to 6 now, okay? So that's what we do. So we get rid of P6 from the free pool. We put it here, and we put this in here, okay? At the same time, since we are doing this is a superscalar processor, we do two things at the same time. At the very same time, we also do the second instruction, okay? So second instructions, we see that x2, but remember that we do this in order, which means that we first do this and then do this. That's why now x2 is mapping to p6. It no longer maps to p2, okay? x3 is mapping to p3. x4 is the destination register. I need a new mapping for it. I'm going to go to this rat table, and I'm going to change 4 to 7, okay? Another thing that you realize is that now I'm also kind of remembering my old destination register here, because I need to free them when the ROB tell me to, right? So when the ROB tell me to free, I'm going to free 2, and I'm going to free 4 in these two particular examples, okay? So here is going to be the kind of renamed logic. Any questions here? Great. And then another thing that I'm going to do is that I need to decode. Again, there is nothing special about decode in this case. I'm going to decode these two guys at this point here in cycle 2. Okay? So now I'm going to go, and then nothing else is changed. So the only thing that is changing is that essentially I get rid of two registers from free pool. I create a new mapping in my rat, and I read these values from my register file. Okay? Now we go to cycle 3, and this is where we're going to do dispatch. Remember, during dispatch, we do two main things. We create a new entry in reservation station and populate the data. We also reserve a line and a row in my ROB and populate the data. Okay? So what should we do? Let's just start talking about reservation station. So we need to dispatch this instruction. We're going to go through my reservation station. Remember, my reservation stations, all the 4 lines were free. So I'm going to pick the first one. This is just a random choice. I'm going to first pick the first one, and I'm going to change the use to 1, because now this line is being used. Okay? Then I'm going to store the opcode into my reservation station. This would be load. Then I'm going to basically populate all these other things. So first thing I'm going to look at is the destination register. Destination register in this case is P6, okay? Important thing that happens here is that immediately once we have a destination register, since this is the register is going to be written to, I need to change the availability of this registers to no, because this is the registers that are going to be used by this instruction. It's going to be updated by this instruction. So in future, we cannot use this register anymore until this instruction is finished, is completed, okay? So that's why I changed 6 to no, because now I know that there is an instruction that use P6 as is the destination register, okay? Then I'm going to populate this with the source register 1, P1. Is it ready or not? I'm going to go through this table and see that X1 is ready. So I'm going to put yes here. The second one is an immediate. As I said, immediate, I can put like random numbers. I'll usually just do X0 or P0, and it's always ready. Since this one also has an immediate, I'm going to put the immediate here, in this case 0. And since this is a memory operation, remember that I said that some ALUs can be used for everything. Some ALUs are dedicated. In this case, I can only use the functional units that is dedicated for memory in this case. So I'm going to put functional unit 2 here, okay? And then, as I said, I'm going to, at the same time, I'm going to save a line in my ROB. So I'm going to change the valid bit of my ROB to 1. I'm going to save the destination register to P6, right? I'm going to save the old destination register, and this is how the number is coming up, right? So I'm going to save old destination register here. I'm going to save the PC to know which instructions. This is going to be my tag, right? So I'm going to save this 100 here. And this will basically tell us that whether this instruction is completed or not. At the beginning, this instruction is not completed, so there's nothing there to be saved. And here in my reservation station, since I reserved the first index, I'm going to put 0 here. Okay? So I'm going to repeat this for the second instruction. So I'm going to change the use bits to 1. This is an opcode add. The destination register is P7. The moment I put P7, I'm going to also change this to no. Then I'm going to do P3. I'm going to check this table and see that P3 is ready. So I'm going to put yes here. I'm going to check P6 and put P6, and then this is where interesting things happens. I can see that P6 is not ready because it's dependent on the previous instruction. So I'm going to put no here. Immediate, I don't care. There's no immediate here. I can either put 0 or I can put some random number. And then I'm going to choose which functional units I'm going to use. Since this is just a generic instruction, I can start from round robin. I can start from this one. I put 0 here. And then again, same thing happens here. Change valid bit, P7, P4, 104, and it's not completed. And I put 1 here. Okay? So this is how I'm going to dispatch an instruction. Question? Yeah. So the question is, since these two things are happening at the same time, and this is kind of dependent on this one, how do we do that? We're going to actually, within one cycle, we're going to do it first and second. So we're going to make sure that we are actually following the order. If you are doing multiple, we're going to do 1, 2, 3, 4. Mm-hmm. Yes. V. So the question is, what is this V? It's valid. Means that that line in ROB is valid or not. Mm-hmm. We're good? Perfect. All right, so we dispatch in cycle 3. At the same time, we also need to rename the next two instructions. Okay, so how do we rename? Again, same story. X4 should be renamed to P7. And then it was P7 here. Okay, so X4 should be P7. X5 should be P5. And the new X5 should be mapped to something new. So we probably change this from 5 to 8. Then for the load, we're going to have X0. X0 can stay P0, same story as before. 0 stays 0. X4 needs to be mapped to another one. So it used to be 7, 4. Now I need to assign some new number. So we'll probably put 9 and 7. Okay. So this is what I'm going to get. Okay. So or is going to P8, P5, P7. And load going to be P9, 0, P0. Okay. So this is what's going to be the new updated table. I'm going to get rid of P7, P8, and P9. Okay. Questions here? All right. Then I'm going to go to cycle 4, and this is when we're going to issue things. By the way, in all of these other cycles, we still want to do issue and complete and retire. The reason that we didn't show that is because there was nothing to issue. Only in cycle 4, we can issue something, because in cycle 3, we put things into our reservation station. Prior to that, our reservation station was empty, so there was nothing to issue. Now in cycle 4, I can issue things, okay? So how do I issue? As I said, I'm going to go through the valid bits, okay? I'm going to see that these two guys are valid. I'm going to start with the first one. I'm going to check these 2 bits. If I see yes and yes, and I see that this FU is 2 and this FU is available, I'm going to issue this instruction, okay? How do I issue it? I'm going to issue it by changing the readiness of the functional unit to no, and changing the use bit to 0. All I need to do is flipping the bits to 0, okay? So I'm going to issue this instruction. Then I'm going to check the second one. And the second one, as you can see, this one is no, so I cannot issue this instruction. So in this particular cycle, I can only issue one instruction to my functional units, okay? So issuing is basically just this, that I get rid of this, and I change this to no. And I'm going to wait another cycle for this instruction to come back, okay? Then at the same time, I need to dispatch. And again, if you remember, dispatching was putting things into here and here. For this one, I put P7 and P5. I check the readiness and I see that P7, for example, is not ready. I also put the P8 here, and I'm going to change P8 to not ready. And I'm going to use another functional unit 1, and then I'm going to create ROB here, and I'm going to move forward. For this one, I'm going to put P9 and P0, yes and yes, P9 here, and this becomes no as well, okay? And I'm going to put ROB3, and I'm going to continue that way, okay? Questions here? Great. So at some point, the instruction will get completed. For example, let's say we assume that the functional units only take one cycle. So for example, this instructions can get completed. What happens is that this becomes yes. So we're going to write 1 to this, okay? And another thing that happens is that this also becomes yes, right? Because now the functional units can be reused. Another thing that happens is that the destination register P6 now can be yes, okay? Yes, so this one can become yes as well, okay? So this one becomes yes, this one becomes yes, and this one becomes yes. And now what will happen is that, so this is all we do for the complete stage, okay? Now we need to issue things. So what will happen is that once I complete this instruction, since now P6 is yes, remember I need to tell my reservation station that, okay, this instruction is completed. So now I update the value. So basically what I do is that I update this, and I need to change this to yes. This is a process we call waking up. So we wake up the reservation station with the new number. So from the complete stage, we're going to forward the value back to my reservation station and tell the reservation stations that, okay, the new value has come. P6 has been updated. So reservation station going to search through these components and see wherever it's CP6, it's going to update the value. I'm going to change this. In this particular case, it's only 1 here. So you're going to change this no to yes, okay? And that's all you need to do for your complete stage, okay? At the same time, the issue now going on. So the issue, remember again, goes through all 3 possibilities, and it sees that, okay, this is yes and yes. Functional unit 0 is also yes. I'm going to issue this. It goes through this one and sees yes and no. Not going to issue this. You're going to see that it's yes and yes. Functional unit 2 is now also yes. So I'm going to issue this as well. Okay, so I'm going to issue 2 new instructions in this particular case. Okay. So I'm going to get rid of these 2. Still, this one remains. And then I'm going to change these 2 guys to no. And then I'm going to also retire. So I'm going to go to the cycle 6. So as you can see in cycle 6, since now I have an instruction that is completed, I can see whether I can retire this or not. If you remember, this was the head of the ROB. Since it's the head of the ROB and it's completed, I can retire this instructions, which means that I move the head of the ROB 1 down. I change the valid bit to 0. And here's the important thing that happens is that I release the old destination register. In this particular case, the old destination register was P2. So I put P2 back into my free pool, okay? And then I'm going to continue. This is all I need to do for retire. For complete, also I see, for example, this instruction is completed. And what I do is that now, since P7 is updated, I'm going to change this to yes. I'm going to change this to yes. I'm going to change this to yes, and so on and so forth. And then I'm going to issue another instruction. Since now this changed to yes, I can issue this instruction. So this instruction also goes to the pipeline, which means that now this needs to be changed to no. And then again, next cycle, I can retire these instructions and put this back into my free pool. And the last 2 instructions are going to be completed. These 2 becomes yes. These 2 becomes yes. And then finally, I retire both of these guys since they are both head of the RB. I'm going to put these 2 guys back. And then as you will see in cycle 9, I'm kind of go back to square 1, right? So
everything is back in free pool, everything is yes, everything is yes, and these guys are all empty. In reality, you're going to have a stream of instructions, right? So they're going to keep instructions going to keep coming. You're going to keep repeating this process over and over again. Okay? All right. So this is kind of it for basics of out-of-order. Next time, we're going to do a little bit more talking about a little bit more advanced topics, such as what happens if there's prediction and so on and so forth. All right? Thank you.